long. When you use Google, you type in immediately, it come out, right? So actually Google, when they start, they know this is the problem. And in fact, nobody knows how to solve it. Even Yahoo at the time, it was the prominent one. They don't have the solution. They use another way. So Google founder, they attack this head on. They know that they cannot do it, but they have to be a bit smart in order to solve it. So the engineer suggests this. Use distributed system. You got a lot of PC, and you got a lot of storage. Okay? So what you do is, let's say your content is this much. You split them, and then you distribute them like this. Okay? And this chunk here is going to be small, alright? Imagine you got maybe Google has a couple 100,000. Okay? So it's going to be small for each one of them, right? And then the PC is not super great, not supercomputer, just normal desktop computer. And you search this small space here. Okay, so let's say I give a keyword, that keyword will be sent to all of them. And all of them will just look into their space on it. Will it be faster? It'll be faster, alright, because I just look for the space that I have. Very small. And everybody is finding it. And then all this result will be sent to the controller, or maybe I'll call it the master, let's say. So the master does not do the job, he just distributes the command to all this PC, and this PC is going to search and then return all the result. Okay, this result is going to be shown to you. Isn't that faster this way? Okay, and of course you can repeat this. Let's say this storage can repeat vertically. So horizontally will be different, vertically will be all the same. Then it will be faster, isn't it? So Google actually attacked this using distributed system, and actually it works. That's why Google become very successful because of this reason. And this is a way also we use in our practical as well. We use storage element on each PC in order to significantly increase the amount of processing speed. Okay? So that is the motivation of parallelism. Actually started with different commercial initiatives, and we use that knowledge in order to use it for another reason or for another purpose, apart from just searching for a website. Okay, so another thing is when you if you can scale, isn't it going to be cheap? Because if you scale vertically, that means you improve the size of storage, you improve the speed of the PC. That means you have to buy a supercomputer. It's going to be expensive, right? But if you scale horizontally, then it'll be cheap. So in terms of performance, you can scale, because no matter how big your complex problem you have, you can actually split them up into multiple PC, right? And you can lower down the cost as well, because you can buy all this off the shelf. Okay, so where do we come from? Actually, we come from batch era. In the batch era, the PC is a powerful PC. We don't have supercomputer at the time. Maybe we're about to come up with a supercomputer. By that time, there is a powerful PC. Sorry, it's not called PC, it's called computer. PC is personal computer. So this computer is not PC. PC haven't existed yet. Personal computer, that means you personally own the computer. In the past, nobody owned computer because it's so expensive. One computer costs you about a couple of millions. Nobody can own it except big company. So they don't have PC, they have mainframe. So mainframe is just like a personal computer, but is shared. Okay, so mainframe is a very powerful computer, and then it has a lot of communication media here. And then you got console. Okay, you have your own console, which is your monitor, your keyboard, your mouse. The same thing here. So everybody is connected to this mainframe, one computer. Okay? So this is the 1970s, sorry, 1980s, 1970s, late 1970s to 1980s. Okay, PC comes about later on, 1980s onwards, until present. Okay, but before this, before 1970s, 1960s, we don't have mainframe. We also have a computer, but that computer is less powerful than mainframe. Mainframe is running like in, not gigahertz, in megahertz. But you can share among it. Actually, the lab in D block, you see upstairs there, you got a lot of PC, right? Last time there's one mainframe. When I was a student, I was using this. It's green in color, the screen. Only one color. We have our own console, we have keyboard, we have mouse. We don't see computer, it's only these three on the desk. And the mainframe is where the lab assistant is sitting there. The lab assistant sitting there, actually, that's where the mainframe is stored. But eventually we remove it because we got into PC era, so you get removed. Actually, during PC era, we still use this. Okay, so before this mainframe, before 1970s, this computer even slower than this. They're running at kilohertz only. They don't have a monitor like this. There's only one terminal, and the terminal is used by the technician. And if you're a programmer, you cannot program directly. You have to go through the technician. So how do you program? You take a card something like this, and then you punch a hole. Oh, sorry, not hole, not one hole, but many holes. And then you pass to the technician. The technician go to the computer, and then use some reader, and you read the card. And then it goes into the memory, and that is your program. So when you punch the hole is the program. You punch the hole in binary. You have to write in machine language. And then you have to wait for turn. So if somebody is already using the computer, you have to wait. So you of course, if you're a professor or student, normally you don't wait, right? You punch, you pass to the technician will tell you, okay, tomorrow I'll give you the result. So tomorrow you come, and then you give you one long list of paper. We don't have monitor, we have printer only. So the printer is going to print, and then you see the result. If you see any error, you punch the hole again, then you wait the next day. It takes so long. Okay, so that is the batch era. Batch means it goes in sequence, one by one. That means I give to you, and then you punch one the technician will do it for you. Okay, and then we move on to this mainframe. Mainframe, we have the console already. So each person can actually write the program, and the mainframe will service immediately. So that is time sharing era. Why? Because this is the first multitasking, time sharing. Before this, there's no multitasking, it's batch eras in sequence, one by one. Then time sharing, this is the first multitasking. Okay, this is done in using mainframe, because the mainframe has their own console. You can actually use it at the same time, but actually it's only using one computer. Everybody is sharing the same computer. So that is time sharing era. One computer, one powerful computer serves all. And then PC comes along, that's the desktop era. At that time, not so popular, we have network already, but not so popular. Network also start about this time as well, but it was expensive. If you want to use the internet, you have to use telephone line. Actually now it's a telephone line. But the data is sent not in digital, sent using sound. So that's why you pick up the phone, you hear the sound, all that kind of sound, right? And it's going to be very slow. The first time when I was using, I think it's only 32 kilobyte per second. And then they upgraded to 64 and then so on and so forth. But before that, it's even slower. I can't remember what it was. And it's very expensive. You have to pay quite a lot just to get this internet connection. Okay? So things have advanced so much already. Now we come into network era. Right now is actually beyond network era already. Right now it's AI era already. Okay, big data and AI. So actually we should fill in the blank down there. Network era is the internet. Now the internet is already saturated. We are going into AI, big data, and right now it's AI era. Okay? So this is the 4 decades, but of course right now it's beyond that already. This is not updated. So the batch era is what I mentioned to you. So you can see that this is the printer where it prints the result. There's no screen. Every of your result is going to be printed on the paper. Okay, so time sharing era where you have, it does not show to you, but the picture is something like that. One very powerful computer, and that is when you got the multi-programming, multitasking happening. This is the time where your P-thread and all that appear. They start developed during this time, 1980s. There's no multi-processor, one processor on it. Okay, but it's a powerful processor. At that time it's powerful. Of course now it's not powerful anymore. At that time 10 megahertz is 20 megahertz is already fast. And then desktop come along. Okay, and network era is at the beginning of a stage, and then we were in the network era. Maybe your father is a network era. Now you are in AI era. Okay, and so that is the history of the computers. Okay, let's look at the computer architecture and also how it changes over time. Okay, the processor that we use, you have of course instructions, and also you got data. And in the past, when we run the program, we run only single program, and it does all the job. Okay, you got the data, and then it processes the data. Now, during late 1980s, in the PC era, late 1980s, Intel came up with the idea of multiple instruction. Single instruction, multiple data. Okay, so all the while, starting from here, we are using single instruction, single data. This is a processor architecture. From here to here, single instruction, single data, and this is also you learn in your assembly language. You learn assembly language, right? It's also single program, single instruction, single data. Unfortunately, they did not teach you the next one, which is a single instruction, multiple data. So we have single instruction, single data. This is the traditional one, all of us learn. And then late 1980s, Intel came out with, actually not Intel, IBM also came out with their own idea, but Intel is the one that popularized in our PC world. Is single data, single instruction, multiple data. So what it does is this: you have one instruction, but then you got different data that you process. Okay. For example, when you do image processing, right? Let's say you want to filter some image. The image is very noisy. You want to filter it, or you want to compress it. Your instruction to compress is the same, but the data is different. Okay? Let's say, for example, your pixel, you know that in order to display color, it needs red, blue, green, right? Yeah? Now, if you want to compress the red, you also have to compress the blue and green also, right? The compression instruction is the same, but the data is 3. Okay? And this 3 data has its own different values. So instead of processing the red, compress one red, compress blue, compress green. So you got 3 steps there. You don't want to do that. You want single instruction, multiple data. When you compress these 3 at the same time. And you can do that because this red, green, blue sit next to one another. The data is close by. So the instruction will read these 3 and then compress at the same time. Okay? So we got this instruction, and Intel has a name for that. I'm not sure whether you heard at that time or not. MMX. Have you heard of this? So these are MMX instruction. What we learn all is without the MMX. Okay? Unfortunately, they did not teach you in your machine assembly language. Actually, they should teach you this. Okay? So otherwise, you learn single instruction, single data, but we have MMX instruction inside our PC. Okay? Before the GPU came about, this was very popular because this is the only way to do parallel computing. Okay? But the parallel computing, of course, is not like GPU. GPU, we got multiple threads. This one, no threads, is at instruction level. So parallelism at instruction level. Okay? Okay, so PC introduced single instruction, multiple data. And then, of course, we have to fill in other gaps as well. Then we have multiple instructions, single data. This one does not exist in PC, unfortunately. But IBM use it in supercomputer and all that. So this one is a more fancy kind of computer. Another one is multiple instruction, multiple data, also not available in PC. Okay, it's only available in supercomputer that designed by IBM or those expensive computer. Okay, they have that. Okay, so it's single instruction, single data, one processor, one instruction, one piece of data. Okay. Multiple. Let's look at this one. Single instruction, multiple data. That means you got one instruction, only one, but the data are split into different parts, and this processor is going to process different part of data, running the same program. Okay, multiple instructions, single data. You got 2 programs, but you're working on the same data. This one is not so popular because in many applications we don't have this kind of need. Maybe this one is useful in engineering. Okay, let's say rockets. They use the same data, but they process for different purpose. One is maybe to know the direction. The other one is to determine the speed. For example, how much power that you need to propel your rocket up. So they use the same data. They have a sensor to sense the data, surrounding data, and then that same data is fed into 2 different programs. One is to control the propeller, the other is to control the direction. Okay. So this one is more specific use. The other one is multiple instruction, multiple data. You got different program running on different computer, and the data is all different as well. This is also very rare, but it's used in application that is maybe expensive kind of application. Okay? These are normally served by IBM. Okay, so these are old computer. This one is before the mainframe. UniVac is before 1960s, and then IBM came up with mainframe, IBM 360. This is a supercomputer. At the time, it was one of the fastest ones, Cray 1. Cray is the scientist who developed it. And these are the most popular mainframe during 1970 to 1980s. It's still used right now. It's used by bank. Okay, why bank use it? Because bank resists modern system because they have all the software there, and the software is so big, they don't dare to touch it because if you touch anything break, they got into trouble. So they still use it, and that's why you hear people are still looking for old programmer who can program Fortran or COBOL. COBOL is very old computer and old language. It was developed during this time, but it's still highly paid, especially bank. If you learn COBOL, you can work in bank and you can earn a lot of money because they are still using this computer. Very funny. Because bank they have so many software inside there and they don't want to touch it, so they're still using this old computer. I'm not sure when they're going to change it. Okay, so this is how it looks like for a single instruction multiple data. You got a lot of data that's come in, and then of course you need to have a processing unit. PU stands for processing unit, and the instruction actually is one instruction. Okay, this is how it looks like. Okay, all the programs are the same, but they are working on different data. And this is the one that we always use because this is the most useful of all. Okay, so OMP use this architecture, MPI. I think this week all of you will learn. Is also using this architecture. And GPU is also using this architecture as well. And this is the most common one. Okay, because we found out that this is most of the problem can be fit into this kind of format in order to solve efficiently and fast. Okay? Including the GPU. So GPU is here. And in fact, all the Cray computer, all the Crays are the supercomputer. It's also working using this format as well. Maybe because of that, that's why we use it here. Okay, this one is not so much in use. Like that I mentioned just now, I talked about the space shuttle, right? So it's used in space shuttle, which is very common in space shuttle, but this only IBM will produce for them, right? And it's going to be very expensive to buy this kind of computer. Okay, this you have multiple instruction. That means your program is all different, and your data is only one data. And you use the sensor data, or of course not only one, maybe a group of it. But then your purpose to compute is for different purpose. Maybe it's to steer the rocket, propel the rocket up, and also for finding your coordinate. Okay, because you need to fly to a certain orbit. You need to make sure that you reach the orbit at a certain period of time. So you have to use all this information, same information, but for different purpose to reach the destination. Okay, this one is used mostly in a supercomputer, multiple instruction, multiple data. That means each computer will be running different program, and they also use different data. And this one most probably is used for simulation or maybe weather forecast. Okay, let's say you want to forecast the weather. Why weather forecast is important? Do you know? First thing is you need to know, especially those extreme climate. There's certain area which has extreme climate. You have to warn the people. Okay. Let's say, for example, there's a tornado coming. So you have to simulate to see whether the tornado will appear at specific period of time. So they use this supercomputer to simulate and to find the path of this tornado. Okay. So that they can clear off and beforehand, because you want to move people away from the path. You have to do several days before, right? So they have to predict the movement of this tornado. So they use this multiple instruction, multiple data, because different part of the computer will compute different part of the area. Okay, so in our serial computer, you got one problem. We can break it down into different parts, and then you solve them using the single processor, although there are different parts, but you have to process them sequential. That's why it's serial computer. That's what we have all the time. Okay, parallel computing, the same problem. You break it down. That means this same problem. You In this case here, you break into 4, and within this 4 here, you break into multiple instructions, and then you feed them to the processor. So here in serial, but vertically is in parallel. Okay, parallel computer, you can do it on a single system, which is what is done by the GPU and also OMP. But you can also do parallel computing using multiple computers, different nodes, okay, and they are connected through the network. And this is what we're going to learn in this week, MPI. I think some of you already learned. But of course, I haven't shown to you how to distribute among different PC yet. We are using on the same single computer, but the same program can be used to run on different nodes on the network. Okay, you don't have to change the code. The code is the same, and we run on different nodes on the network. Okay, so it can achieve parallel computing, and this is the most cost-effective one. Okay, because you can scale horizontally. Okay, you can increase the core here, but there's a limit there. All right. Of course, GPU is exceptional. It's quite a lot of cost there, but it's very simple core. Running very high speed, but it's a simple core. If you want a more complex core like the Intel processor, then most probably you cannot increase beyond 32. 64 maybe is the upper critical number already. Okay, so here repeat again what we have talked about. If you work together, you can see that when you build the building, if everybody is doing their own parts, you can make faster. Huh? Okay, so it's the same idea we borrow in our computer world as well. The same thing here, you can see the tractor work on only one lane, but they can cover quite a lot of space here. So imagine here is all data, and you have a lot of processor there, and each one of them will grab only that specific data, and they can process at the same time and finish faster. Huh? So what kind of problem that you want to solve? Real world problem, more complex problem. Like for example, if physicists, they are interested in finding out, is there anything smaller than what we know? Before we know that it was atom, but we found out it's not atom that's smallest. We found out there's heat, boson, got quarks, got so many other smaller particles, which make up the electron and also neutron and whatsoever. So they are interested in simulation, so they use this parallel computing in order to do that. Maybe that one is fancy things. But what other things that is more important to us, that maybe the one that we can see? Maybe in medical field, right? Recently I heard there's a medical field which use AI. What they did was they used simulation. In the past, if they want to find the drugs for a cancer patient, they have to do it one by one, and it's going to be a very lengthy process. By the time the patient already died, because it takes so many years just to find the drugs, right? So they apply AI. How did they do it? And they can go in weeks only. They can find the solution iteratively. So what they did was they take a cell, and then they culture it, the cancer cell. They put in the cell culture. They grow it on a plate, and then they apply different drugs, and then they put it under a camera. The AI is going to see the morphology. Morphology means the shape of the cancer cell, whether it progresses or it shrinks or it stays stagnant. It doesn't grow. And then you pick and choose, and then you tell the medical doctor, okay, this drug is effective, this drug is effective. And then you come up with an algorithm to suggest to the doctor, okay, I found out this combination of drugs works well. This ratio and this ratio. Why don't you try this? So you come up with another series. And then the doctor will use that answer or the solution, and then mix the drugs again, and then take the cell, culture it again, and then grow it and show it to the AI. And the AI will pick and choose the best out of this solution. And this iterative cycle go on and on until they find the best drug. So this drug is personalized drug, and we can do it now. Because one thing they find about cancer is this: it works for you, it doesn't work for the other person. Okay, it works for some part of your organ, it doesn't work for another part of your organ. Okay, now we can do personalized drug, meaning that if you come in, you got cancer, they know that if they give you the drugs that work for other people, it will not work for you. So they use this technique. Of course, it is still a trial stage. It's called personal drug, and they can do it because they got AI. AI use spell computing, right? And then, and they can go through this cycle within a very short time. Okay, they can test, they can immediately find out what are the combinations that is good. Actually, it's a real case. It happened in this, I know it because I read in the article. The patient is a young boy in Singapore. Okay, and one of the university, I can't remember which university, one of the university in Singapore, they did this. So they're able to recover the boy. But unfortunately, of course, the cancer recurs. When it recurs, it becomes stronger. Okay, every time it recurs, it becomes stronger. So they have to find another drugs. They did it multiple times. I think three times. But the cancer kept on recurring. But unfortunately, the boy died. But it's a big promising one because if you can personalize like this, that means it's good for the patient, right? Because right now, the doctor, if they don't personalize, what they do? They take the strongest drug and give it to you. Maybe you die because of the drug, not because of cancer. Okay, that's the reason why they come up with personal drug. So there's a real problem that is being used. Okay. Another one is using paracomputing also. The one that I heard is to find the bacteria that can compose plastic. Okay, the best that they found, it was some solution. It was not using bacteria, it was using chemical. That's the best solution. They put in, I think it took about 1 month in order to decompose it to save materials from plastic. So the scientists want to find out if they can use computer to find the best bacteria to do the same. So they found some bacteria after they do the simulation and all that. So the computer will suggest, okay, this bacteria seems to be potential bacteria, why not you try? So they try in a lab and they found out that it's better than the chemical one. Then they use AI in order to identify which are the best bacteria to choose. Because there are so many bacteria, we cannot expect the scientists to use all the bacteria and test in the lab, right? It takes a very long time. So what they do, they use AI. The AI will simulate using the enzyme that they excrete. They find out whether this enzyme is able to decompose the plastic or not. Okay, so they identify, they will point out, okay, this bacterial group I think is quite good. You can try this. So the scientists use that solution in order to test on the bacteria, and they found actually it's a good idea because it actually beaten the best chemical to decompose the plastic. Okay, so that is another example. Actually, you can search on the internet. They have a lot of this floating in the internet. Those that use computing to solve real world one. Okay, so we have that, and of course in banking also the same thing. Banking, we have computers all needs to communicate with one another, and then they have to process independently. So we use this since at the beginning of the dawn of the computer era. Just that we do not realize it, right? Once you have network and then you have computer, it's basically a distributed system already. Okay, so this the architecture of the processor. You got the core, and then you can see very clearly that is level 3 cache. Level 2, level 1 is inside this column. Okay. It's not really clearly shown, and here maybe it shows. PU stand for processing unit. You got a lot of processing unit there, and you can see L2 there. This L2 is in the middle. And at the center here, that is the matrix, the communication matrix. That is the backbone of the network. So the processor has the network as well. Okay, so this backbone will route the messages from the different PU to different PU, or to grab the data from the level 2 cache. Down below there, you can see the network circuit, as well as SERDES. SERDES is serial and deserialized. Serialized and deserialized. That means from parallel is sent in serial, and when you receive in serial, and then you come back as parallel. That is used by your network. That's hardware. We don't have to know about it. Okay, the motivation we already discussed. Now we want to talk about why it is important right now, and why it is the speed is accelerating very fast. Everybody is adopting this parallel computing. Okay, one of the reasons is because we have a standardized parallel environment libraries, like for example OMP, MPI. These are freely accessible by all of you. Okay, and we can buy GPU off the shelf. In the past we cannot buy, but right now we can buy GPU. And it's not like very expensive in terms of millions. A couple of thousand, you can buy a GPU already. Okay, so it's affordable. Okay, so that actually speed up the adoption of parallel computing. Okay, another one is because of the internet, you can share this information. Like for example, you learn about OMP and all that, you learn from the internet, right? You can go to the internet and books as well. So improve and increase the speed of adoption. And of course, there's also the need of using it as well. For example, to solve AI problem. And of course, GPU initially when it got started is for 3D graphics. So 3D graphics gaming actually spur the interest of using GPU. Now is AI. Okay, so the parallelism, of course, we already reached like the limit already. That's why we have to go sideways. Instead of increase vertically, we have to go horizontally. In the past, we can always shrink the transistor down smaller and smaller. But right now, we cannot shrink further because the transistor, the wire across, do you know how many atoms? You can fit 10 atoms. Okay, and the current technology, the width of the transistor, right? You can fit 10 atoms. How much more can you reduce? Eventually, you cannot reduce further, right? At one point, you will reach the limit. So they say we cannot increase the clock speed, we cannot increase or shrink down further the transistor. What can we do? We have to go sideways. Sideways means we have to do parallel computing. Okay? So this is one of the reasons. Of course, because of that reason, we also look for other alternatives, like say for example using light. Okay, light is faster by a number of times. There's experiment that shows light can do logic computing as well, and it's about 1,000 times faster. Okay, so there's one opportunities using light as computing instead of using electrical signal. The second one that is also promising is using carbon. Right now we use silicon, right? So right now they want to use carbon sheet. one sheet of carbon. And you can create transistor on carbon as well. Okay, it's low power, it's 1,000 times more efficient, 1,000 times faster. You can switch faster because it has a lower, what do you call it, potential. It has a lower voltage potential, so you need lower voltage in order to switch on and off, and you can switch faster, 1,000 times faster. But carbon is very hard to produce, manufacture. They can do it in the lab, but you want to do mass scale, they have to build quite a lot of things, and it can be very costly. So it's not mature yet. So carbon is another one, and now is quantum computing. So that's the third one. Okay, quantum computing is very weird, and we don't program usually like this. If you find paracomputing is weird, you go to quantum computing, is even weirder. Okay, because quantum computing, the bits, it can be in all state. Okay, until you read it, then only you fall into the specific state. That means it can find all the solution at one time. When you read it, then only you fall into one state, and then you can read the answer. So that is quite kind of weird, because we never imagine things can happen like this, right? That's why, have you heard of Schrodinger cat in physics? There's a cat in a box, and you put poison in there, and then they ask you whether the cat is alive or dead. In quantum world, the cat is dead and alive at the same time. Until you open and see it, then only it will be dead or alive. So people are questioning right now, is this world real or not? Because this thing cannot happen, right? Okay, quantum computing, and why they ask this question? Because we have quantum computer, and it's real. Okay, the quantum bit can be in all state. That means it has the solution all the while. Until you watch it, then only you can see the answer. Once you start to read, it will collapse to one answer. And that is kind of weird. Of course, scientists is trying to find out how this thing works. They don't understand. But right now we are using it for our purpose, even though we don't understand. Okay? Okay, so that's quantum computer. It's also another promising one, and Google is doing research on it, but they put on hold because of China. Because they're afraid China steal the idea and also the knowledge. They're afraid that China become a superpower in the future. This is a trade war. So they don't allow any further. Maybe they allow just that they don't announce it. Maybe they tell us that Google stopped, but I don't think Google stopped at all. Okay, Google is still doing it, but they do it in secrecy. Okay, maybe in the future, maybe your children is going to see quantum computer, really quantum computer. Okay, just like what we start from here. At that time, we are still here, right? So our quantum computer is still here. Okay, maybe your great-grandchildren, you will see a quantum computer maybe in a cloud. Okay, the quantum computer is very big, just like our old computer, and you have to chill down to certain temperature. Okay, because right now we have to. Quantum computer, one thing, when you read, it has a lot of noise. So high temperature, higher noise. So I have to chill down to minus 80 degrees or minus 90 degrees. Nobody can have this as a desktop, right? Because you have to fridge. You have a fridge here next to the computer. So it's not ideal. Okay, so what is the level of parallelism that you can have? You have many levels. You have a job level, which is the task level. So that's why we have multitasking. We can also have at program level. The program itself, we can create it into different tasks, all right? So we got at the job level and then program level. So program level, your different part of your code is going to be run by different computer or different cores. So you achieve parallelism that way. Okay, another level is parallelism level happen in the instruction, which is this one, MMX. Okay, so this one is GPU. Okay, this one is multitasking on computers. So we have this long time ago. We have this also quite a while ago at instruction level, because Intel was using MMX, right? So the parallelism happened at the instruction level, and then came along the GPU. Okay, GPU is level at the and parallelism at program level. Different part of the program run different code, maybe different same code but different data. Okay, and then we have also bits level. This one actually exists in our single instruction, single data as well, but this is at bits level, and also it can happen inside MMX as well. Okay, so this is the lowest level. It's after instruction, the lowest one is the bit level. That means you can process the bit at the same time. For example, if I want to end this binary, let's say 0, 1, 1, 0, 1. I want to end with this number, right? Do you end one by one? Of course, the primitive computer, you have to end one by one. But our computer, we have 8 bits, isn't it? So when we end all the 8 bits in parallel. Actually, we already done it in here, right? So this is what it means, okay? So we can do at bit level, okay, at instruction level, like this, okay, at program level, using threads in GPU, and at job level, which is multiple computers like this, okay? So we can do parallelism at different levels. Okay, in parallel computer, the most important part of actually one of the most important part, apart from the processing unit, is also the memory. So the memory is because you need to store the data you need to process. So we have parallel computing architecture, which is UMA, is uniform memory access. You got the CPU surrounding the memory. That means this memory is shared, and they have equal access or privilege to this memory. Nobody has any advantage. Okay, so this is uniform memory access. We can also have non-uniform memory access, like this, NUMA. Okay, for example, in this case here, this CPU has equal access to this memory. Okay, they are one cluster. This CPU, this group of CPU has equal access to this memory. This one also the same thing, this one the same thing. But if this CPU wants to use this memory, then it's not equal. Okay? Because the privilege is given to this CPU rather than this CPU. Of course, this CPU can access, but you have to go through this network in order to get to this memory. So this is non-uniform memory access. Uniform for itself, but to others, no, it's not non-uniform. That means if I want to access, I have to think whether it is good to access or not. Because I do not have the same speed as this CPU here. Because I have to go through this network to get to this CPU. Okay, so this is more scalable than this. Of course, everybody wants this, but of course we know it's not scalable. We have to do this. Okay, so if you want to increase the number of cores, you have to do it this way. You have separate memory. This memory is shared. It's shared among all, but it's non-uniform, meaning that it's uniform among this group, but not uniform to this group. This CPU has less privilege to access this memory. It's either slow, or it does not have the authority to access, or you have to think twice before you store your data here, while your processing program is here. Okay? Most probably you want to migrate your program to here in order to expedite it. Okay, so that is on the single system. But how about over the network? Yeah, you can also over the network, but this one is even slower because this bus interconnect is fast. I'm talking about petabit per second here. Okay, because this is on the silicon itself, and the distance is very small. Okay, in micrometers, so they are running in petabit per second. You can reach that amount already. Peta. So we got mega, giga. After giga, tera. After tera is peta. Okay. After peta is exa. Okay. Every time you increase is 1,000-fold. Okay, 1,000 times more. Okay, so peta is quite large. Right? It's already beyond tera. Tera is power 12. Peta is power 15. Okay, and in fact our network, the speed is already reaching peta. Now going to exa. Okay, so this one is distributed memory. In distributed memory, this is slower than this architecture. Okay, this architecture is also called NUMA. Okay, except that this on the level. Okay, and you can have something like this as well, where you got GPU combined with the CPU. Okay, so you can have different kind of architecture. This is hybrid distributed shared memory system using similar concept as NUMA. So how many you have? NUMA, and then distributed memory, hybrid distributed shared memory. Okay, this one we have learned in the class before, parallel program models. We share the memory without using network. Okay, so we share this memory by, here show the process. Of course, we have thread as well. I always tell you they are the same, but actually there are slight differences, but we can view them as the same. Okay, the only thing that if people ask you, let's say you go for interview, what is the difference between these two? If you do multi-processing, the task switching is going to be slow. The task switching in thread is faster because it's lightweight. Okay, this one is heavyweight, this one is lightweight. Okay, you can see here heavyweight and lightweight. Okay, so the task switching is faster. This one is faster than this. Okay. And another thing is process, meaning that this process is different program, completely different program. Maybe this is one browser, this is other program. So the process run different program. But the threads, each process can have multiple threads. So the thread is actually inside the process. Okay. And MPI actually is using this model. GPU is using this model. Okay, this thread model. Okay, the MPI is going to learn this this week. We can have multiple machines, and the task can be broken down into what you see here, and it can run by different processors. So, like this machine here, you can have multiple threads and also multiple processors as well. Okay, and then it can communicate between these tasks using communication message passing. And across this machine also using the same message passing. So at the moment in the lab, we are using a single machine. We are using message passing. The message passing is between the processors on the same machine. But the same program, you don't have to change it. You just tell MPI exec, those who learn MPI exec, which computer reside in which cluster. Okay, you just give it a list and then you spread out. You don't have to change the code. You just tell MPI how to spread out the task. And the MPI is going to do it for you. You're going to assign the machine and run the process and then assign the data. And then you work on the data and then you get the data, just like what I showed you here. Okay, so this model, the MPI, actually borrowed from Google, the model in Google. Okay, so you split into multiple tasks and then you run on different machine. And then when you, of course, you have to send the data. And when they process the data, you receive the data back. Okay, some of you maybe haven't learned yet. Scatter gather, maybe you will learn next week. Okay, scatter gather is something like what I mentioned to you. Yeah. But here it's not scatter, it's just gather. Because the data is already on the machine. If let's say the data is not on the machine, then you have to scatter. Scatter means the main process or the master process has to distribute the data for the other PC or the other process to execute. Process the data. Okay, and of course here, because we use this model, single instruction, multiple data, so you will have data that can be processed in parallel. Okay, you just need to split the data into multiple chunks and then assign it to the process. And you can see here, the data is different, 1, 25, 26, 50, but the program is the same. Okay, so we can run in parallel by doing this data parallel model. Okay, most of the time, as I said before, we have multiple data and it's processed by our processor. And that processor can run single program or it can run different program. So if it is running the same program, then different data, you can see this data 1, data 2, data 3, data 4, but it's run by different processors running the same program. Or they work on different data, but they're also running different program. Okay, so there is a multiple program, multiple data. So we have some kind of similarities. So we got processor, which is single instruction, single data. We got single instruction, multiple data. We got multiple instruction, single data. We got multiple instruction, multiple data. Okay. So this is the CPU architecture. Okay, CPU architecture, that means it's hard-coded into the processor itself. It can do this. Okay, and it can do it at its instruction level. Parallelism at instruction level. Okay? What we are talking here in this slide is something similar, but at job level. So this one is job level. Using the platform that we discussed, for example, MPI, OMP, GPU and all that, right? So same thing. Here we don't call single instruction, we call single program, single data. Okay, single program, multiple data. Multiple program, single data. Multiple program, multiple data. So it's synonym here, but actually you're talking at different parallelism level. This one at instruction level, we are talking about the CPU processor itself, able to do this at instruction level. Now we are talking about at job level. Okay, you got the program that is running, not single instruction, but single program. A program consisting of multiple instructions. Okay, so there's some kind of analogy there. Okay. Okay, another thing is when you design your parallel programming, what you need to consider is also whether it's easy to program and how to do it. You can do it semi-automatic, automatic, or manual. Okay, OMP can do semi-automatic. How does it do it? For example, the OMP parallel 4, you put the 4 keyword, right? So actually it does the parallel computing behind. Okay, it do it for you. That means you use exactly the single processor code. You just append the pragma OMP parallel 4, and it can automatically do it in parallel for you. But sometimes you cannot do it. Okay, you cannot. It's not automatic or semi-automatic. You have to manually do it. For example, GPU. In GPU, you have to do it yourself. You have to understand how the architecture works. Then you have to program just to run on the GPU. And I'll show to you later on how to do that. So there is some that can be automatically done You just feed in the single program, and then you do it for you. Okay, you convert it for you to this, or this. So this one needs the compiler. Okay, so MP actually can help you, but it's not fully automatic, it's semi-automatic. MPI is the worst one. MPI you have to do it manually. GPU also the same thing, you have to do manually. Okay, the most frequently that you target is the loop, because the loop is the most frequently executed code. Okay, now if you can break down the loop into multiple parts where you can run them in parallel, then you can speed up the computing system. Okay. Alright, there are some problems which you can easily parallelize. Some problem you cannot parallelize at all. Okay, those that it can be easy is like what is going to be shown below. I'll show to you later on. They are independent of one another, then you can parallelize. The problem down below there, this is not easy, or maybe cannot. Little to no parallelism. For example, is this Fibonacci series. Some of you come to me and ask me, can I do Fibonacci series computing? Can, but you don't see any performance gain. Okay, and of course Fibonacci is very simple. You don't do that as assignment. Because this one, you cannot parallelize at all. Little to no parallelism. Why? Because the data is dependent on the previous data. Okay? The Fibonacci series, right? If you want to, and so on and so forth, if you want to find the next sequence, you have to rely on the previous data. For example, in this case here, this 2 plus 3, you get this, right? In order to get this 8, you plus this 2. You get the 8. So suppose you want to run in parallel, you assign one thread to each one of them. But each thread have to wait for one another. So you run in serial also, even though they run in parallel, because they have to wait for one another. Right? So here, there is no little to no parallelism that you can achieve from here, because it's tightly dependent on the previous data. All of them depend on one another. Okay? What you want is they don't depend on one another. If they don't depend on one another, then you can achieve great parallelism. And I'll show you some example. Maybe not down below. Maybe next week. Okay, so if let's say you can achieve parallelism, right? You can parallelize them. So how do you achieve them? There are 2 ways. Most of the time we do the first one, decomposition, domain decomposition. This is what we do always in our lab. Okay. The second one we seldom do. Okay. So what is domain decomposition? So we have a program, and then we are asked how to design a parallel program. Right? And this is what we do always in the lab. Or we ask you, okay, how do you parallelize? You have to go and think, put pragma here, put pragma there, right? Okay, so for MP, the same thing here. So we have to look at the program and the problem and see how we can break it down into chunks and run them in parallel. So we can decompose them into, we have 2 models of decomposition. The first one is domain decomposition. The second one is function decomposition. Okay, let's look at the domain decomposition, because this is the one that we use always in our lab. Okay, domain decomposition, we are looking at the data. Function decomposition or functional decomposition, we look at the code. Okay, so here we focus on the data. This one we focus on the code. Okay, what is the meaning of decompose? Decompose, that means break down. Okay, domain decomposition means you break down the data. Functional decomposition means you break down the program. Okay, that is what it means. Okay, so the domain decomposition, the data, this is a problem set. You can break it down into multiple parts, right? And then you assign them to different tasks. So that's what we always do in a class. So we are doing domain decomposition on the wall. But how do we do it? I always teach you only one technique. I teach you this one. Actually, two of them. This one. 1D. So, actually we are doing this one rather than this one. But let's look at this one because it's easy. So you got multiple blocks, problem. You break down into equal parts and then you assign each one to the task. Okay? So let's say this is, the data is huge, let's say 100,000, okay? If I have 10 threads, or maybe 100 threads, if I decompose using blocks, what it means is, I look at the number here, and I take this, divide by this, how much I get? 1,000, right? So each block here is 1,000. The size is 1,000, 1,000, 1,000. Okay? And thread number 0, thread 0 is going to handle all this. From 0 to 999. Thread 1 is going to handle that, thread 2 is going to handle that, thread 3 is going to handle that, thread 4, this is thread 99. This is in between. Okay? Is that clear? So that is block 1D. 1D means one dimension. Block decomposition. The one that we always use in the lab is actually cyclic. Cyclic, the next one. Is 1D cyclic. How do we do it? If we have the same 1,000. Let's say we got 100 threads, we're going to split them into 100 altogether. And each thread is going to be assigned here. Thread 0, thread 1, thread 2, thread 3, until thread 99. Okay? But this is only 100. There are many more, right? So we repeat. Isn't that what we are doing in a class? It's like this, isn't it? Is it correct? So we have, again, we use the same thread applied to here. So thread 0, thread 1, thread 2, thread 3, and so on and so forth, until thread 99. And then because we haven't finished yet, we have to repeat again and again. That's why we put that in the for loop. Right? So actually we can, we always do this, but if we don't want to do this also we can do this. We never try. But if you try, you can actually solve the same problem. The way we decompose is different. Okay, domain decomposition means the technique of decomposition. How do you solve? Do you want to solve this way or you want to solve this way? Okay, ideally they are the same. But there is some penalty here. Okay, some penalty here. Penalty, that means some overhead if you do this. Okay, that's why we use these techniques most of the time. Okay, this has something to do with memory penalty. We can do this way, but we don't encourage. Okay, unless the memory does not introduce penalty. Okay, if it doesn't introduce penalty, you can do it this way. Okay. Since I told you that there's a penalty, yes, it happens for single processor, single system. Single system, they have memory penalty, that's why we don't do this. But if you are doing distributed system, then you prefer to do this rather than this. Why? Let's say, for example, this storage I told you, right? Google was using this block decomposition. In our OMP, we use this. Why Google use this? Because this data is residing inside the storage, right? If let's say they do this, then it's a bit hard because this PC has to ask the other PC to give the data because it's not holding the data. You have to ask it. So there's a penalty in communication there. Okay, so it depends on the system. So that's why designing parallel computing, you have to look at your architecture, see whether it fit nicely. We use this in our computer system because there's a memory penalty. I'll explain to you why the memory penalty if you do this. It's going to be slower if you do this. It's going to be faster if you do this. But in distributed system, it's going to be slower if you do this. It's going to be faster if you do this. Okay? Because your data in the storage is split nicely like this. That's why you prefer to do block. You prefer to do cyclic for single process. So you got two ways for one dimension. In 2D and multiple dimension, you can split equally. It's the same technique like what I mentioned to you. In 2D, you can split block in vertically or horizontally. Okay? Because two dimension, right? X and Y. So you can split it in Y direction or split it in X direction. Or you can do block. You can split it like this also can. Right? So that is 2D. Or you can do cyclic. Cyclic means this small block here, you split them up into multiple threads. Just like what we did here, the cyclic here. Okay? So this block here is not done by one thread, but multiple threads at the same time. And then the same thread is going to be applied here, here, and here in Y direction. Okay? You can also do in X direction. Same like this, and compared to this cyclic. So instead of doing block like this by one thread, you split this block into multiple threads. Okay? Each thread is going to handle it. And then you repeat this many times in X direction. Okay? Or you can split it two dimension like this area here, X and Y, is done by one thread, second thread, third thread, fourth thread. You can also split them up like this in boxes like that. And this one is, we're going to use this technique, the second technique, in GPU, in two dimensions. In fact, my exercise, the one that deals with graphics, turning color image to grayscale, right? I'm using this technique, cyclic, in GPU. And the size I use is 32 by 32. So 32 in X, and 32 thread in Y. Okay, so I have this thread split into like that. Okay, and then apply one time, and then it goes to the next until you complete the width of the picture, and then go down like this. Okay, until you solve all the problem. Okay, so 32 by 32, if you multiply them, you get about 124 threads. So I use 124 threads in one go, solve that picture. Okay, and each of them solve one pixel. Right? So I use 32 by 32. You can check the code. If you see 32, that 32 is this 32 here. And I make them what do you call it? Symmetry. Okay, you can change. You can change 64 and different value here. Okay. Okay. Why I choose 32? Because the maximum number of threads I can have is only this much. So I split them like this. Okay. So I was using cyclic to solve this problem. Okay, we will look at this in lecture 8 or lecture 9. I think lecture 8. Okay. So we decompose the data. 1D, 2D, of course, and we got 3D as well. GPU can do 3D, but it's not shown here. But you can imagine how it looks like. But it's 3 dimension. Okay. Okay. Another one which is not so common is functional decomposition. Functional decomposition, you decompose the function. Okay. Our OMP GPU, we don't use this. We normally use decompose the data rather than function, because we run single program, remember? Okay, so running single program, normally we use domain decomposition. But if you use thread, if thread can support multi-cores, at the moment I know that it doesn't support, but it support, then we can use it for function decomposition. We can assign one task to do one function. Let's say this task do this function, this task do another function, another task do another function. Okay, and they are independent function. They can be processing the same data or different data, depending on your what kind of model that you use. Okay, if you are using multiple programs, single data, that means your decomposing it into functionals, and then you're working on the same data. If your model is multiple program, multiple data, then you're using functional decomposition, and each of the tasks is actually working on different data. Okay. So functional decomposition is suitable for. Okay, I just highlight it. Single program, single data, and single program, multiple data. Of course, this one is out. This one is domain decomposition. Okay, domain decomposition. If you have multiple program, multiple data, or single program, multiple data, okay, this one is out. This one is functional decomposition. Okay. Okay, that's what you see here. Domain decomposition, you look at the data is the one that is multiple. Functional decomposition, you look at the program is the one that is multiple. Okay? This one is out, this one is out. So these two, decomposition is suitable for these two models. Okay? Okay, why this functional decomposition is not suitable for single program, multiple multiple program, multiple data. So actually it's suitable for this one, because also MP here, I made mistake. Okay? This one is single data, sorry, mistake. Okay? So this one is also applicable to this. Okay, it's also applicable to this. So this is applicable to this too, and this data domain decomposition is also suitable for this because of this. Okay, so domain decomposition suitable for single program, multiple data because of the multiple data. It's also suitable for multiple program, multiple data because of this multiple data. All right. How about functional decomposition? It's only suitable for these two. Okay, multiple program, single data, multiple program, multiple data. Okay, this one is excluded because there is no parallel computing. Okay, single program, single data is single core, single threads. Okay, just now I talk about what is suitable, what is easy, what is difficult, right? So here shows to you, the easiest one is the top. The top one, you don't need at all to communicate with one another, and also you don't have to wait for one another, right? For example, if I ask you to change that square, black and white, to become the inverse, or invert the color. Black become white, white become black. And I assign one thread to each cell. Are they going to execute in parallel? And they don't have to wait for one another. They are not dependent on one another. So this is the easiest one. Okay? If your problem is like this, you're lucky. Okay? Because not all problem is like this case. If your problem is Fibonacci, no chance at all. Okay? You cannot do parallel computing. But sometimes it's in the middle. You cannot do it easily because there are depending on one another, but not fully like Fibonacci, but some kind. Because some of you, I think, asked me about a problem related to molecular simulation. Okay, you want to see how the molecule vibrate in three-dimensional space. Okay, that is very suitable for power computing because you can simulate that. And that problem is the second part problem. It's in between. Okay, so you have easy problem. You got hard problem, very hard. This one is impossible. And you also have in between. So in between is the one in the middle, at the bottom. So you need to actually rely on the data next to one another, but not too far. For example, in this case here, we're going to simulate two-dimensional heat diffusion. That means how the heat propagates. We heat it up at the center, and then we want to study or want to simulate how this heat propagates to the rest of this body or this entity. Okay, so we can simulate it, right? You can use single core or single thread to simulate this. That means you have to compute all. But we also can do parallel computing. Okay, so we decompose this using this technique, domain decomposition. Okay, so the space is the data. So we assign like this checker box here. Each thread is going to be handling this box there, the box that you see there. Okay, so this one big box, two big box, and this thread is going to handle a number of pixels inside. Okay, or space. Now, if this heat you propagate from the center, isn't it? So if this guy who wants to compete, he has to know the neighbor, the close neighbor. What is the heat, so that he can compute its own heat, right? Its own temperature, that's what I mean. So it needs to know the surrounding temperature. Okay? But how about the guy over here? Does it need to know at the center here? No, it needs to know within a surrounding. Maybe it will need it, but very small chance. Okay, the effect is actually quite small. Okay, depending on the distance. So we'll be looking at the neighbor only. Okay, so in this case here, it depends on the neighbor. It doesn't depend on all. It depends on the neighbor only. So in this case here is in between. Okay, because you need to wait for the neighbor, a few of your neighbor. You don't have to wait for all your neighbor. If you have to wait for all your neighbor, then it becomes a hard problem. Alright? If you have to rely on the result of your neighbors only, then it becomes somewhere in between easy and hard. If you don't rely on your neighbor at all, it becomes this, the simplest of all. Alright? So it depends on what kind of problem. And of course, we want the problem to be like this, but not all problem is like this. Most of the problem is in between, like this kind of problem. Okay? Okay, for this actually, there's a lot of text inside there, and the previous lecturer copied and paste, but then it does not tell where it is, and I found it. Maybe I'll share to you later. The text is here. Oh, sorry. Not found. Maybe it detected I accessed yesterday. I cannot access. What is the problem? Was not found. I cannot access. Maybe I'll pass to you later. Here are the ones. Okay, actually it comes from the same source. This guy also using the same source. Actually, there are many universities. Just now I got it from different universities. If you want to read the text, I mean the details, it's all here. This one actually don't have all, it has some. Okay, so what did we see just now? We talked about functional decomposition and all that. Okay, so let's have a look at the. So communication overhead, latency bandwidth, visibility, communication, synchronous or asynchronous, the scope of communication, efficiency of the communication. Okay, so when you design your parallel program, you have to look into these factors, the factors that you need to consider. Okay, first thing is the most, I think, highly important is the communication overhead. We need to find out whether is there any communication overhead or not. For example, here, if I want to do this decomposition, is there any overhead? Yes, because the storage I hold for all of this, but it's used by different process. I'm thread 0 or process 0, but my data is needed by other process. So I need to send, right? Correct or not? So there is overhead, communication overhead. All right. So when you choose this model, you have to look at the overhead. If you choose this, your communication overhead is high. If you choose this, your communication overhead is low. You understand? Okay, the details you want to learn more, I mean, is explained here, cost of communication. Okay. Another one is the latency, and we actually related to this communication overhead. For example, if I ask, of course you have to send to me, right? But when I ask you, are you free at that time? Right? So I have to compose the message and send to you. So I use bandwidth, okay, because I use the network. I also have to suffer the latency because I have to prepare the message to send to you. It's not immediate, okay? So I have to look into that as well. To decrease the latency, what do? The process itself do the job because it does not need to communicate. Once you need to communicate, you introduce latency. Okay, and if you use the network's communication, you have bandwidth problem because if you don't have enough bandwidth, then you cannot communicate fast enough, right? Let's say your data plan is only, what is the data plan? 10 megabit per second. 1 megabit, you don't know. Most probably it's at least 1 megabit per second now, right? But in the past, when I was younger, 32 kilobit per second only. Cool. So imagine if 32 kilobit per second and I want to use this model. No way. Okay? But if my bandwidth is terabit per second, then it's okay. Okay, so you have to look at your bandwidth. Alright? If let's say you don't want to do this, you have no choice, you have to do this, and you have to use the network, look at your bandwidth. If you have terabit per second, okay, no problem. But if you have 32 kilobit per second, no, don't do that. Alright? So you better change your strategy to this. So that is this consideration that you have to think about. Okay, the third one is not so clear. It's about the visibility of the communication. How visible is it? Do you do it yourself or you use the platform? If you use MPI, the communication is hidden. So you do not know how it is communicating. So you do not know the cost. If you do it yourself, it's visible to you. So it's easy for you to access. Okay? So you have to consider that as well. You cannot say, oh, MPI do it for me, so I just don't care. Okay? But sometimes you need to find out whether there's any overhead or not. But most of the time, MPI is clever. It can reorganize itself, and then it will know where to store the data up front, so that it does not need to use the bandwidth so much. Okay, so you're relying on the MPI to do it for you. Okay, the fourth one is synchronous or asynchronous communication. What it means is this. When I communicate or send the data to you, do I need to wait or block? Okay? If I send the data, I don't have to wait, I can do my job. That means I run in parallel, right? So non-blocking is called. Then it's good. That is asynchronous. But most of the time you cannot do that. You have to wait. For example, if you do this, you send the request, you ask for the neighbor's temperature because you want to calculate your temperature. And if you don't have the neighbor temperature, you have to wait, isn't it? Because you cannot proceed. Right? So that is synchronous. Okay? If you send the data and you can proceed to do your job, you're not blocked, then it's asynchronous communication. That means you communicate, you don't have to wait for the result. Okay? So you have to look into this as well. Are you able to do asynchronous communication? If it is okay, then you can proceed. If it is not okay, you have to do synchronous and to check whether any performance degradation that is bad. Then you improve on it. Right? Okay, the scope of communication is basically do you do one-to-one, one-to-many, many-to-one. Okay, so this is like broadcast, scatter, gather, okay, or reduction. And the efficiency of communication, it depends on, it's basically on how you communicate efficiently. For example, if I want to send the data, do I send the raw data to you? Or I compress first, then I send? Because you want to find whether it's efficient or not. If I compress and send, maybe it's better, right? Because I'm powerful enough to compress fast. Okay, because it's hardware accelerated. I can compress using hardware, not software. So I can compress very fast. And when I send very little data. So I save on the memory. Okay, I also save on the latency because I have the processing power to compress very quickly using hardware accelerator. Okay, so you have to consider all this in order to determine which design is best. Okay. Okay, I don't have enough time. I'm going to talk about fine-grained parallelism, coarse-grained parallelism next week, and then I'll go ahead to explain about the GPU. Actually, I want to explain this part here, this one, which is related to this, on how the GPU look at the problem, and then we compute the ID of the thread, because this is the part which is quite important. It will come out in exam. Okay, that's why I want to talk about this. But I don't have time today. I'll discuss this next week, okay? See very clearly, right? 7, 8, 8, 6, 7, 3. Okay, this is a code. Okay, those who are not able to take attendance, please come down here. Don't go back yet. Okay, come down here. I can help you. Take your attendance. Okay.